Hi everyone, this is Becky, and in this video we are going to take a closer look at the Bohr model of the atom. So the goals for this video are to discuss what emission spectra reveal about electron placement in atoms, and to connect the evidence, so emission spectra, to a new atomic model, which is the Bohr model or the solar system model of the atom. Okay. So just a quick review. Before Bohr, remember that we've been working with this idea of a nuclear model where we have the nucleus in the center, which we now know contains protons and neutrons, and is the mass and the positive charge of the atom. And remember that that nucleus is teeny, teeny, tiny relative to the size of the atom. The atom is mostly empty space. And remember that those electrons that we know exist, negatively charged, tiny particles, have very little mass relative to the size of the nucleus, and that they are really, really far away from that nucleus, like 10 to the fifth, like 6 or 5 orders of magnitude far away from the nucleus compared to the size of the nucleus itself. So they're really far away, and they're on the outside. We talked about this, and that neutral atoms have the same number of protons and electrons, and ions have gained or lost electrons. But we haven't really talked about what exactly is happening with the electrons within the atom. We've said that they're far away and that they're moving around, but we haven't really specified any further than that. And the nuclear model and the Rutherford model doesn't actually specify further than that. But we have some evidence, or we have some things that we can use to explain where electrons are. So in class today, or last time we met, you took a close look at these things called emission spectra. And so remember, this is how neon lights work. So essentially we take a gaseous sample of an element, and we pass electricity through it, and we get this clear, distinct color. And what we're looking at is for hydrogen. And when we break down that light that is emitted, we see it comes in very distinct frequencies of light. Only very distinct wavelengths are produced. All right, and this is true for every element, although every element does produce different wavelengths. They all produce very specific wavelengths. It's not a spectrum, it's distinct wavelengths of light. And so how can we explain this, right? The way that we explain this is to say that electrons can only exist in specific energy levels away from the nucleus, right? So if I have an electron and it starts out here, right, the electron absorbs some energy, and it jumps up to n equals 2, right? So this is absorbing energy. Same thing here, right? This electron is absorbing energy, jumping up further away from the nucleus. It eventually is going to fall back down. When it falls back down, it's going to emit light in the form of a photon, right? And so the energy that we see is only the energy, the frequencies are only the frequencies that correspond to the electron moving between these very specific energy levels, right? So the energy that an electron can have within an atom is what we call quantized, meaning it can only take specific values. A good way to think about this is to think about your potential energy. For example, when you're standing on a ramp, so if this is you on a ramp versus you on a flight of stairs, right? So on a ramp, your potential energy is not quantized. You can have, remember, gravitational potential energy, mass times gravity times height. So because on a ramp, you can be at any height along this ramp, your potential energy can take any value on a ramp. But on stairs, you can only have very specific height values, right? You can be on the bottom stair, you can be on the first stair, but you can't be in between the bottom stair and the first stair, right? You can't be in between stairs. So your potential energy can only correspond to specific heights, which means that your potential energy is quantized. Same deal here for electrons. Electrons can't be everywhere. They can only be at specific distances away from the nucleus, or specific, what we're calling energy levels, which you can kind of think about as corresponding to distances away from the nucleus. So the energy of these electrons is quantized, and so they can only be here, or here, or here, but they can't be in between. Like, you can't get an electron in the middle. And that makes sense given what we see with emission spectra. If electrons could be everywhere, we would see all frequencies of light being emitted, because all transitions would be permitted which means that we'd see everything. But we don't see everything. We see very specific values, which says that only specific energy transitions are permitted, which means that electrons can only be in specific locations around the nucleus. So what that leaves us with is this idea of the Bohr model, which basically says that electrons are moving in circular orbits around the nucleus, and that only specific orbits of certain radii are allowed. So there's only specific energy orbits, and those are the only ones that are allowed. Think about this like planets and suns, but only specific distances away from the sun are allowed for planets to exist. Same thing. And that energy is emitted or absorbed by electrons only as the electron changes from one allowed energy state to another. So only when we're going from, say, for example, n equals 1 to n equals 2, we can absorb and emit energy from that transition, but otherwise we're not going to absorb or emit energy. And that energy is going to be emitted as light. So this is what we're left with, right? We have the nucleus in the center, and we have electrons kind of orbiting around the nucleus at different energy levels. And because different energy levels have different radii, they can hold a different number of electrons depending on how far away they are. So the bigger the energy level, the more electrons it can hold, and the further away from the nucleus it is. Also called the solar system model because it really does look like a solar system. So when we think about this model of the atom, there are some real limitations with it. It works and the math works really, really well for the energy levels for hydrogen. But as soon as you add a second electron to the system, the math just falls apart. It doesn't work. So it's kind of okay, but not really describing the behavior of electrons in multi-electron systems. Also, he had some weird, funky initial assumptions that we can talk about if you want to come talk more about this. And he really couldn't explain why it is that electrons don't fall into the nucleus. It makes sense. You think about electrons as being negatively charged, protons and the nucleus as being positively charged. Electrons should fall in. They don't. Why don't they? Bohr couldn't explain that. But the key thing here, and the thing that is really important here, is that this idea that electrons are in quantized energy levels, and that turns out to be true and still true today. And this is the first evidence we have to suggest that, the first model that suggests that electrons exist in specific discrete energy levels, and that the energy is involved in the electron transitions between energy levels. We are going to kind of stop here and really just think about electrons within energy levels and not really further refine what an energy level looks like or where electrons are within that energy level. Remember that Heisenberg said that we don't actually know where electrons are, and we can't ever fundamentally know because of the wave-particle duality and because of the uncertainty in the measurement of the momentum of an electron as being bigger than the size of the atom, which means we have no clue where they are. So we don't actually know where they are. We do know that they don't orbit, so they do not orbit. But they are in these energy levels, and so we're going to kind of stop there. We know more about what energy levels look like. We know more about the structure within energy levels. And if you want to talk more about that, your teacher or I will be happy to talk to you more about what we know further about the structure of energy levels. But for right now, here's where we're going to stop with this idea of electrons being in energy levels. Okay, so for the question at the end of the video, what I would like you to think about is, why do you think that these energy level transitions, so the frequencies of light that are emitted in the emission spectra, are unique for each element? Why isn't that energy level 1 is always the same energy and energy level, why isn't it that energy level 1 is always the same energy and energy level 2 is always the same energy? That's my question to you, because they're not. So why do you think it is that they're not? What could affect that? All right, so think about it. Jot down your thoughts, bring them with you to class the next time we meet. We'll see you then.